In a previous video, we have seen conventional method of measuring voltage, like we have seen PMMC, and today let's start with DVMs. This presentation contains the introduction of DVM, basic block diagram, why we need electronic voltmeters, how EVM solves circuit loading, construction and working of electronic voltmeters, and in the next video we will see ramp type, integrated type and successive approximation type DVMs, because we are seeing these all types in depth. So let's begin with what is electronic voltmeter. Before understanding first slide, we will recall the conventional method of measuring voltage. Like we have placed two magnets and we were generating uniform magnet field. And in the there was a between coil and we were giving it load. And due to that current flowing and generation of two torques, controlling torque and deflecting torque, the pointer scale was moving and it was showing the voltage. And yes, it was the conventional method for measuring analog voltmeters. Now, let's understand why we need to change and why we switch to electronic voltmeters. In a practical electronic system, especially in instrumentation and control circuits, precise voltage measurement is very critical. So, electronic voltmeters are widely used in such scenarios due to their high input impedance and sensitivities. For example, let's understand this by one sensor called LM35. Okay, so suppose we before going to the understanding these two passages, I will explain you okay, what is why we need digital voltmeters. So suppose we have temperature sensor called LM35 here, measuring output voltage from a temperature sensor like LM35. Now suppose our sensor is providing 10 millivolt per centigrade. Okay, so causing a conventional voltmeter would load the circuit and alter the reading. When we connect this sensor with the analog voltmeter, so analog voltmeter needs some current load to work the circuit. So due to loading of the circuit, there is a change of actual voltage of the signal. So the voltage we are getting will not be accurate. But in EVM draws a negligible current and accurately measures such low voltages without disturbing the source. What it means to say, there was almost no current, no loading due to very high input resistor. So it looks as the voltage without disturbing the circuit. So what voltage we are getting? It is accurate reading. Like as we want in a biomedical instruments, temperature sensor circuits, like in ECG, we require highly accurate instruments. So we cannot use analog voltmeters there. This is like, see, an EVM, however, draws a negligible current and accurately measures such low voltage without disturbing the source. This is essential in embedded system, sensor interference, and biomedical instruments where signals are weak and highly sensitive. In conventional method, like in analog voltmeter, we were seeing that due to uniform magnetic field, low voltage detection was also not possible. It was also one of the limitation of the analog voltmeters. So we need this digital electronic voltmeters. When measuring the output of a sensor like LM35, which gives only 10 millivolt per centigrade, a conventional analog meter with a low input impedance draws a current from the source sensor and forming voltage divider that reduces the voltage being measured. Instead of reading 300 milliwatt at 30 degrees Celsius, analog voltmeter might be showing around 273 millivolt, causing error due to current. But in contrast, when we put high impedance in the circuit, due to that there is a negligible current. So it ensures the actual voltage measurement without disturbing the sensor output. Like we can see the rough diagram of the electronic voltmeters, where we can see attenuator, amplifier, ADC, digital decoder, and display. So let us discuss. When we get any input signal, we will see the ramp type, integrating type, and also successive approximation type, where we use comparator for working this circuit, for as it's a principle of working. So in what is the work of attenuator? When we send the signal to comparator, before that attenuator rectifies or amplifies the original signal according to uh, get desired output. So the amplifier and rectifier both are the part of attenuator. We use it in a high frequency to attenuate the frequency. Like, see, here we are giving input voltage and it will go to amplifier or rectifier as said attenuator. And after the operation of signal, it will go to ADC, like analog to digital converter, where we get this analog signal as the output of in the form of BCD. Okay, and that BCD goes to digital decoder, where this BCD value is converted into a readable format that we can read it, and that finally displays into display. So we can use a 7-segment display for the digital as a digital decoder. So it can convert BCD value into readable format. And other decoders are 7-segment display, LCD, and other visual readout system. Suppose ADC output is 0101. So, which is 5 decimal in decimal. So, display will show 5 because we are using here 7-segment decoder. So again, what is the need of electronic voltmeter? So we have discussed, we will see it again in more detail. Conventional voltmeters like PMMC draw current from the circuit to move the pointer. This means they extract power from the various circuit they are measuring. This is known as circuit loading. So why it's bad? When you connect such voltmeter across a low voltage or high input impedance circuit, the voltmeter alters the actual voltage you are trying to measure, as we have seen. This results in inaccurate readings, especially when circuit has sensitive or small signal levels. So we cannot use this in a biomedical instrument or other applications when we desired very accurate voltage as output. So, how DVM solves this problem? The electronic voltmeter use amplifier which have very high input impedance in mega ohms. So, due to very high input impedance, we nullify the current. So, we get accurate output voltage. Very low current draw. This means they don't disturb the circuits and we can get accurate voltage readings even for a very small signals like in a microvolt or millivolt range. Let's discuss about testing in a mobile circuit. Let's some practical examples. While repairing a mobile phone motherboard, a voltage circuit test points may be low as a 1.2 volt or zero point 0.8 volt. Using a conventional analog meters can disturb the IC behavior or even cause malfunctions because it's not made up to detect very small voltage. It can't. So EVM are used in a search to measure low voltage accurately without affecting circuit operations. So it is the practical examples where we cannot use the conventional method. So again, we will see here we are giving input voltage and it will go to ADC. First, it will go to attenuator where operation of the signal is done. Then it is goes to analog to digital converter. Again, it goes to signal processing device where ADC converts the in a BCD format and that goes to the digital display, that 7-segment display or LCD, which is readable format. Here we are showing the DVM in a practical circuit. We can see this is the display, this is the sensor, and ADCs and everything are connected to the circuit. In electronic voltmeters, the input voltage, often very small, is first amplified using high gain differential amplifier or an op-amp. We'll see in detail. This amplification is crucial because weak signals in a millivolt or microwatt range cannot directly drive display system or analog meters effectively. So we are using op-amp. By amplifying the signal, we ensure that even the smallest voltage change becomes measurable, which is greatly improve the sensitivity and accuracy. Here we are discussing about very small voltage, but if there is a very high input voltage, the system, what our discussion is become contrast. In analog electronic voltmeters, the amplified voltage is typically applied to PMMC, which gives a linear deflection proportional to the system. So we cannot get the desired accuracy. Since PMMC meters work only with DC, any AC input is rectified before amplification. In digital voltmeter, the amplified voltage is fed into ADC, which is then digitize the signal and sends it to digital display unit, usually an LED or LCD screen. Amplification ensures that the entire measurement system works over wide range of input voltages with high accuracy and linear response. In digital voltmeter, the input voltage is first amplified. We have discussed if necessary to bring it within the operating range of ADC, which typically accepts the voltage in the range of 0 to 5 watt. The amplified analog voltage is then fed to ADC, which converts the continuous voltage value into binary number like BCD. This digital output is processed and displayed as a readable voltage value on the numerical display such as 7-segment or LCD. Since PMMC meter work only with AC AC input is rectified before amplification. In digital voltmeter, the amplified voltage is fed into ADC and ADC converts into binary value, and binary value then gets converted to readable form. Here we can see the diagram of the electronic voltmeter. That very simple. This electronic voltmeter contains all the component. Amplification ensures that the entire measurement system works over a wide range of input voltage with a high accuracy and linear response. The input voltage is first amplified, and ADC we have discussed this, okay? High input impedance in electronic voltmeter is essential to prevent circuit loading. In instrumentation and control system, accurate voltage and resistance measurement are fundamentals for monitoring and automation tasks. When we work with any PLC or SCADA system, so our basic requirement is the accurate measurement of the voltage and resistance. Ramp type DVMs. Let's discuss all three types of EVM in a brief. In the next lecture, we'll see in detail. Ramp type electronic voltmeters operated by measuring the time taken for a linear voltage ramp to reach the input voltage level, making them suitable for low-cost application where speed is not crucial. In a ramp type electronic voltmeter, we can see comparator, a ramp signal, and one comparator connected to ground and a ramp signal. So we will see that what the attenuator attends the input voltage signal according to the comparator. So how it works, we will see that in detail. But we should remember that the ramp type is only suitable for low-cost applications where speed is not crucial. In integrating type DVMs, especially like dual slope DVMs, are preferred in industrial environments due to their excellent noise rejection ratio, making them ideal for resistance measurement in a noisy plant condition or for integrated sensor outputs like RTDs. Random noises, which fluctuates quickly and irregularly, tends to average out to near zero over the integration period. High frequency noise component gets suppressed naturally. So it acts as a low pass filter for fast transient systems. Successive approximation DVMs offer high speed and high resolution conversions, the bestest version of the all EVM for my side, making them ideal for real-time control system and PLC-based monitoring where rapid and accurate feedback is essential. In practice, these methods are employed in a process control for the temperature, pressure, and flow monitoring by converting sensor resistance into digital signals for precise control decisions. So this is the ramp type DVM. We will see in a next lecture in a detail. So what we have seen in today's video is what is electronic voltmeter, the components of electronic voltmeter, why we need electronic voltmeter over conventional method of voltage measurement, and construction and working of the EVMs. So in brief, we have seen that first input voltage goes to op-amp, where attenuator, where it gets amplified or rectified according to the next comparator, and then it goes to ADC, where analog to digital conversion is happened. The output we get in a BCD format, in a binary format. Then, according to 7-segment or LCD display, then it is decoded and we can see on the display the output. And we have also learned that conventional method of measuring voltage is not suitable for a low voltage applications because of they change the actual voltage because of the current passing through the circuit is very high. Also, we have seen the circuit of the DVM, and also we have discussed the sum of the very basic of ramp type, integrated type, and successive approximation type DVMs when to use. In the next video, we will see ramp type, integrated type, and successive approximation type electronic voltmeters in detail.